Hello, calculus fans. All right, we're going to estimate this integral, the integral from 0 to 2 of dx over 1 plus x squared using the trapezoidal rule. Now, this is actually an integral that we could evaluate exactly because we know an antiderivative of 1 over 1 plus x squared. So this is really just going to be for illustrative purposes. So how large should we choose n so that we are guaranteed that the error in using the trapezoidal rule is less than 10 to the 6th power? All right, so before we carry on with this question, let's establish some ground rules for what we're going to be using our computer for. When computing error bounds, let's say that a computer can be used for the following. It can be used for computing derivatives, and it can be used for arithmetic, including computing roots. However, let's say that we can't use a computer to approximate numbers like pi and e. We need to use known bounds on these numbers. For instance, we know that e is smaller than 3. We know that pi is smaller than 4, things like that. All right, let's let f of x equals 1 over 1 plus x squared. The computer will tell us that the second derivative of this function is 6x squared minus 2 all over 1 plus x squared quantity cubed. So what we need is to find k, which is going to be an upper bound on the absolute value of f double prime of x on the interval from 0 to 2, which was the interval of integration. Now we know that on the interval from 0 to 2, the absolute value of 6x squared minus 2 is less than the absolute value of 6x squared plus the absolute value of negative 2. We're just using the triangle inequality here. And of course, we don't need that minus sign anymore since that's an absolute value. And because 6x squared is increasing on the interval from 0 to 2, then the absolute value of 6x squared is smaller than 6 times 2 squared plus 2. Anytime we have an increasing function, we can just plug in the right endpoint to give an upper bound on that function. And so this whole thing is equal to 26. Now, if we look at the absolute value of the denominator, that's bigger than 1 and smaller than 125. And that comes from just knowing, again, that this is an increasing function. So we have an upper bound on the numerator and a lower bound on the denominator. That gives us an upper bound altogether on f double prime of x, absolute value. It's going to be no bigger than 26. So when we're looking for an upper bound on a fraction, we can take an upper bound on the numerator and a lower bound on the denominator. Now, it's certainly possible that we could find a better bound on f double prime of x, but this is going to work for a bound. We're not necessarily looking for the best possible bound. We're just looking for a bound. All right, so we're going to choose k equals 26, a equals 0, and b equals 2. Then, here's what we get. The absolute value of the error in using the trapezoidal rule is smaller than 26 times 2 minus 0 to the third power all over 12n squared. And we want this to be smaller than 10 to the minus 6. So what we're going to do is we're going to take that inequality and solve for n. So when we simplify a little bit, we have 26 times 8 over 12n squared. Let's solve for n. So we just move things around a little bit. If we take a square root, we'll get n is bigger than 4,320.5. And so all we have to do is choose any value of n which is bigger than 4,321. And what we'll want to do is prove that this bound on n guarantees that the absolute error in using the trapezoidal rule is smaller than 10 to the minus 6. Keep in mind that we found n. Now we have to prove that n is good. All right, so we know that the error in the trapezoid rule is smaller than 26 times 2 minus 0 to the third power all over 12n squared. We're picking a value of n that's at least 4321, and n is in the denominator, so we get another bound that looks like this, 26 times 8 over 12 times 4321 squared. If we simplify all this, we'll get 52 over 56,013,123. And now it's fairly straightforward to see that this expression is smaller than 10 to the minus 6, which is what we wanted to prove. Okay, that's all for now.